Jacobian matrix is a matrix containing the partial derivatives of a function whose input and output are both vectors. Hessian matrix contains the second derivatives of a function whose input has multiple dimensions. We will now learn how can we find these matrices. In this example, we will find the Jacobian matrix of a function that maps a vector of length 2 to the vector of the same length. The first element of the output will be the product of both elements of the input vector, summed with 2 times the second element of the input vector. The second element of the output will be 2 times the product of the first element and the squared second element of the input vector. We can see the formula for calculating the individual elements of the Jacobian matrix on the slide. The index I corresponds to the row of the matrix. The index j corresponds to the column. Solving an example will make it clear how we use this formula. The element in the first row of the first column of the Jacobian matrix will be the partial derivative of the function for the first output element. With respect to the first element of the input vector, the element in the first row of the second column will be the partial derivative of the first output function with respect to the second element of the input vector. And so on. Rest of the calculations are simple. We will now find a Hessian matrix for a function that sums the squares of the 2 elements of its input vector. Elements of the Hessian matrix are given by the formula displayed on the slide. For example, in the first row of the first column of the Hessian matrix, we find the second partial derivative of our function with respect to the first element of the input vector. In the first row of the second column, we find the partial derivative of the function with respect to second element, and then the first element of the input vector. Similar procedure is applied for finding the rest of the elements of the Hessian matrix. When we have a function whose second partial derivatives are continuous, the order of partial derivation can be swapped. We can see that the top right and the bottom left elements of the Hessian matrix have the same result for such functions. This can result in the symmetry of the matrix, which is often quite useful.